A warm welcome to session 2 and the completion of session 2, and we are coming for session 3. So warm welcome for session 3 in chemical kinetics. Of course, the first 2 sessions we have discussed in detail the basic things of like rate of reaction, factors affecting rate of reaction. Of course, in the last class we could find out what is a rate determining step. Then we said about the rate law. Then we came to a conclusion of order of reaction. Then we discussed molecularity of reaction, and then I think we ended up in a order and molecularity differences we learned. And coming to the session 3 of chapter chemical kinetics, today we are going to discuss about integrated rate equations. We also call differential rate equation, also we call integrated rate equations, a very important topic in the examination point of view. Okay, so the question will be derive rate constant of a zero order reaction, derive rate constant of a zero order reaction. If I go back to the last class and just recreate from there, what is the order of a reaction? Just sum of the powers of the rate expression, sum of the powers of a rate law. You just add the exponents, then you get the order of a reaction. So you want to write the order, you want to find the rate expression. To find the rate expression, you need to find out the experimental facts, the mechanism. So now what is a zero order reaction? Definition. What is zero order? We say the rate of the reaction is proportional to zero power. The rate of a reaction is proportional to zero power of the concentration of the reactant. That is called as zero order reaction. Now why the power is zero? I will try to explain with few examples in the later stage of the class. Okay. Now that is the rate of the reaction is proportional to zero power of the concentration of the reactant. Let us consider the reaction, a reactant R giving a product P. So consider typical reaction R giving P, that is reactant R giving a product P. You know, rate of reaction is proportional to R in square bracket, that is molar concentration of R to the power 0 according to definition. Now rate is equal to, whenever we remove the proportionality, we replace the constant K. I think we have learned in session 2, R to the power 0. Anything to the power 0 is always equal to 1. The rate of the reactant is always minus sign, minus dr by dt is equal to K. Now transposing the minus sign, dr is equal to minus K dt. I have taken dt cross multiplied and we have taken it K dt. This is a basic thing. Now what we do, we apply integration. So integrating both the sides. So when I integrate the above equation, I will get R, integration of dr is R. A constant cannot be integrated, that is minus K T. Integration of dt is T plus I. Now what is the new factor I has come, new term I has introduced. We say I is called constant of integration. Whenever we perform integration, we have to end up with plus I. The plus I is called the constant of integration. So we have got equation 1, we got a new term I is nothing but constant of integration. Moving further, at time t is equal to 0. That means the concentration of a reactant R, the molar concentration of a reactant R is R naught. What is R naught? Where R naught is the initial concentration of the reactant. Remember always here, the time t, the reaction not yet started, time t is equal to 0. The concentration of R is R naught. What is R naught? R naught is the initial concentration of the reactant. Substituting the above value in equation 1, we will go back to equation 1, in the place of R, R naught minus is equal to minus K, time t is equal to 0. So I substitute 0 plus I. So R naught is equal to I, that is I is equal to R naught. So we got the value of I. Further we say, we will substitute the value of I in equation 1. When I substitute the value of I in equation 1, R is equal to minus Kt plus R naught, with the value of I is R naught. Now transpose, that is minus Kt becomes Kt, R becomes minus, R becomes here R becomes minus R, then what is the derivation now? We want to derive the rate constant, that is K. So, K is equal to R naught minus R by T, where R naught is initial concentration, R is the concentration by T. This is the derivation of the rate constant of zero order reaction. So, this will be for 2 marks. So, this is our final conclusion of the derived rate constant of a zero order reaction, because you know K is a rate constant. So, K is equal to R naught minus R by T. Moving further, we do find out the half life, we call T half life of a zero order reaction. The half life of a reaction is just the time taken, very important for us, the time in which the concentration of the reactant to 1/2 of its initial concentration. What is the initial concentration? Initial concentration is R naught. So, what is half life? The half life of a reaction, the time taken to reduce to half of its initial concentration, that is known as half life. So, we want to find half life of a zero order reaction. The rate constant of a zero order reaction, just now we have derived K is equal to R naught minus R by T. Now, we know that K is equal to R naught minus R by T. Now, what is R? R is half of R naught, that is R naught by 2. Now, what is time? Time T is T half. Substitute this in the equation now. K is equal to R naught minus R naught by 2 by T half. If you take the LCM, that is 2 R naught minus R naught by 2, you get R naught by 2. T half and K comes to the numerator, the denominator. So, T half, the 2 again comes to the denominator. T half is equal to R naught by 2K. So, T half is equal to R naught by 2K. Now, we come to the half life of a zero order reaction is directly proportional to initial concentration. What is R naught? R naught is the initial concentration of the reactant and inversely proportional to rate constant. Remember, T half is proportional to R naught, directly proportional to R naught, but inversely proportional to K. What is K? K is a rate constant. So, definition of half life is very simple, time taken to reduce to half of its initial concentration. So, we could also find the half life of a zero order reaction. So, derive the rate constant of a first zero order reaction, derive half life of a zero order reaction. Both the derivations are very, very important. The statement which I told you at the end is also very much important. The half life of a zero order reaction is directly proportional to initial concentration and inversely proportional to the rate constant. Now, the derivation of the rate constant of first order reaction. What is the first order reaction? The rate of a reaction is proportional to the first power of the molar concentration of the reactant. What we discussed, zero order, the zeroth power, first order, that is first power of the molar concentration of the reactant. Let us consider a reactant R giving a product P. That means rate proportional to R to the power 1, because first power of the molar concentration of the reactant, rate is equal to K R. K, because R to the power 1 is R itself, molar concentration of R. Now, rate is equal to minus dr by dt. Definition says decrease in concentration of the reactant minus dr by dt is equal to K into molar concentration of R. Now, transposing minus sign, dr by R is equal to minus K dt, cross multiplying dt, bringing R, same term dr by R is equal to minus K dt. Integrating both the sides, integration of dr by R is equal to minus K, integration of dt, because constant cannot be integrated, Now, integration of dr by R we call ln R, because we are not converted to base 10. So, we will convert it as we move to end of the derivation and multiply with the number 2.303. Till then, wait for some time. So, ln R is equal to minus Kt plus I. Call this equation 1. I told you earlier, whenever you perform integration, you must always end with I, and I is called constant of integration. Now, when time t is equal to 0, we can say when time t is equal to 0, R is equal to R naught, where R naught is the initial concentration of the reactant. Substitute the value in equation 1. So, ln r becomes ln r naught minus k time t is equal to 0 plus I. We got a value of I is ln r naught. Now substitute the value of I in equation 1. What is equation 1? Ln r is equal to minus kt plus I. Substitute the value of I in equation 1. Ln r is equal to minus kt plus ln r naught. Kt is equal to ln r naught minus ln r. If you learned about log, it's a log a minus log b is log a by b. Log a minus log b is log a by b. So k, because I need to derive the rate constant of first order, k is the rate constant of first order, k is equal to 1 by t, log a minus log b is log a by b, ln r naught minus r, ln r naught by r. Now multiplying the factor by 2.303, you may ask me why should I multiply 2.303? Whenever I want to convert log base 10, I must multiply into 2.303. Therefore, the final derivation becomes k is equal to 2.303 by t log r naught by r, where r naught is the initial concentration, r is the concentration at a time particular time t. So, log r naught by r. This is our derivation, which is very important, frequently asked in the examination, that is derive the rate constant of first order reaction. So, we said first order, the first power of the molar concentration of the reactant, and we move till here. Our final derivation is equal to, that is k is equal to 2.303 by t, that is log r naught by r. Now, moving a little more further, as we discussed about half life of a zero order reaction, we can also find out half life of first order reaction. The definition of half life, the time taken to reduce to half of its initial concentration. So, we need to find T half for first order also. We need to find T half of first order also. Therefore, the K is equal to, we know that K is equal to 2.303 by T log R naught by R. Now, when I substitute at time T is equal to T of time taken reduced to half of its initial concentration, T is equal to T of R naught is equal to R naught by 2. Or we can, this R is equal to R naught by 2, the time taken to half of its initial concentration. Now, as I substitute here, K is equal to 2.03 by T half log R naught by 2. Now, this R naught goes to numerator, R naught and R naught gets cancelled, T half goes to cross multiplication, K comes to denominator, T half is equal to 2.03 by K log 2. So, T half is equal to 2.03 by K log 2. Log 2 value is 0.3010. So, T half is equal to, when you multiply the numerator, it becomes 0.693 by K. So, the half life of a first order reaction is T half is equal to 0.693 by K. Remember, these two formulas, the two derivations are very, very important to solve the numericals. One is the rate constant of first order reaction, K is equal to 2.03 by T log R naught by R. Another is T half is equal to 0.693 by K, which is half life of a first order reaction. These two derivations are important in the examination point of view. Derive the rate constant of first order reaction, derive the half life of first order reaction. So, as we now discuss about unit of, we just finished derivation of rate constant of a zero order and derivation of rate constant of first order. Now, as we move towards the unit of rate constant of a zero order reaction, we know that R reactant R giving a product P and rate is directly proportional to R to the power 0, right. Then we say rate is equal to K, it is for zero order, rate is equal to K. That is, what is rate? Concentration by time. So, we go further, that we say concentration by time. That is what we are trying to help you here, we are trying to explain here. See here, rate is equal to K, K is equal to dr by dt. What is R? R is concentration, concentration is always mole per liter. I told you molarity. There are 4 ways to explain the concentration: molarity, molality, mass percent, mole fraction. And we are trying to discuss about molarity. What is molarity? Number of moles of a solute dissolved in volume of solution in liter, therefore mole per liter. If you go back to first PUC, amount of substance always in mole, so mole per liter. mole per liter, that is we discussed here dr by dt. I know we know mole per liter by second and mole per liter per second. That is the rate constant, unit of rate constant of zero order reaction is what? Mole per liter per second. So this is our, just we finished our derivation. From there we have come to K. K is the rate constant, dr by dt, dr is mole per liter second and mole per liter per second. That is the unit of the rate constant of a zero order. Now what is the unit of rate constant of first order? Now we know rate, again the same thing, now rate is directly proportional to r to the power 1. R to the power 1, if I remove the proportionally, rate is equal to k r to the power 1 and k is equal to rate by r to the power 1. Now you know rate is nothing but here, rate is nothing but mole per liter, rate is nothing but mole per liter per second and r is mole per liter, r is mole per liter. Now coming to a point here, so k is equal to rate by r. What is rate? Concentration by time, concentration is mole per liter by second, so it is mole per liter per second. Therefore we substitute here k is equal to rate by r, mole per liter per second, concentration is mole per liter. So you know mole per liter and mole per liter remains only per second. Therefore the unit of rate constant of first order reaction is per second. So whenever they state the concentration of the rate of the rate of the reaction, the concentration of rate constant of a reaction is per second, remember it is first order. If they say the concentration of rate constant is mole per liter per second, remember it is zero order. So in the numerical part it is very important for us to know, knowing the unit we can say which order is the reaction, and if we say which order you must know to write the unit of the rate of the reaction. Therefore mole per liter per second and per second are the unit of the rate constant of a zero order and the unit of rate constant of the first order. Now coming to the complicated topic, that is pseudo first order reaction, false first order reaction. Now what is the false first order? Why is a false first order reaction? I think when I was discussing about the order, I have told 0, I wrote in some of the reactions, I wrote 0 for one of the reactant, and I told you I will explain it later. So now I am trying to explain it. What is this pseudo false first order reaction? A second order reaction which confirms the first order kinetics is called pseudo first order reaction. You can ask me, sir, what about another reactant? There are two reactants. Why one of the reactant is not involved in the reaction, or what is the reason? What is the reason? Why does it follow? Even though it is second order but follows first order kinetics, what is the reason? Now if I go back to the basic definition, what is rate of a reaction? It is change in concentration of the reactant. Now if any one of the reactant does not change its concentration or it remains the same, that means it has not involved or participated or took part in a chemical reaction. So it has no right to decide the rate of reaction. Let us go back to the practical aspects. So it has no right to decide the rate of the reaction. That means one of the reactant, either it is in larger extent or the concentration has remained the same. Other words, it has not taken part in the reaction, and therefore it has no right to decide the rate of the reaction. Therefore coming to a point, when one of the reactant is present in large excess, then change in the concentration of the reactant is negligible. Negligible means you don't consider it. Maybe a very minute change in concentration, a smaller extent. Therefore, and does not alter the rate of reaction. The reactant does not alter the rate of reaction. It remains the same because it is negligible and it is present in larger extent. Negligible, the concentration of the reactant is negligible. Therefore, CH3COC2H5 ethyl methyl ester, when I undergo hydrolysis, addition of water, it forms acetic acid and ethanol. But when I write the rate, I found the concentration of water is negligible, or water does not alter the rate of reaction, or we say it is present in larger extent. Therefore, I write rate is equal to K ethyl methyl ester CHCOC2H5 to the power 1 water to the power 0. And that's why I told you, a second order confirms first order kinetics. Want to write the order? What is the order? Order is 1 plus 0, that is equal to 1. Similarly, when I take sucrose, C12 explained to O11 plus water, it forms glucose and fructose. Now what has happened? In this reaction, rate is equal to K, C12 explained to O11 to the power 1 and water to the power 0. That means when I could write the rate, that is K into C12 H20 to O11 plus H2O, we write the order is equal to 1 plus 0, that is equal to 1. Therefore, it is called a pseudo first order reaction. In examination point of view, they ask to define a pseudo first order reaction, or what is a pseudo first order reaction? Question mark. Give example. You can give any one of the example. The idea, the reason behind is that when one of the reactant is in larger extent, present in larger extent and does not participate or does not alter the rate of reaction, that means it has no right to decide the rate of a reaction, therefore it follows pseudo first order reaction. So temperature dependence of rate of reaction, or temperature dependence on, we can say, on rate of a reaction. Now I told you there are 4 factors which have played an important role or affecting the rate of reaction. I told nature of the reactant, concentration and temperature and catalyst. Just a point to be noted here. As I increase temperature, the rate constant of a reaction also increases. That means the rate of a chemical reaction is largely depends on temperature. Temperature plays an important role to decide the rate of a reaction. And how does it affect? What is the increase in times? Does it increase or decrease? How many time it increases? So we say here, rate of a reaction increases with the temperature. Point number 2, it affects. Point number 2, it increases the rate with temperature. It has been observed that for a chemical reaction, rate constant increases 2 to 3 times by 10 degree rise in temperature. You just increase the temperature of 10 degrees Celsius, that rate constant increases 2 to 3 times. Kt plus 10 by Kt. 10 degree rise in temperature, the rate constant increases 2 to 3 times. This ratio is also called, the rate is also called temperature coefficient. It's also called temperature coefficient. That means the ratio of rate constant is called temperature coefficient. That means you are very clear. Of course, in the next session, I will try to bring about a plot of the graph and explain definitely how we can come to conclusion the temperature affects the rate of a reaction. How we can come to a conclusion the temperature increases the rate of reaction, I will explain to you in the next session. But today, how does it affect the rate constant? 2 to 3 times, just an increase of 10 degrees Celsius. That is how the temperature affects. Of course, we will discuss in the next class. Now, Arrhenius equation, sometimes they ask in the exam, write Arrhenius equation, explain the terms. Derivation part is not there, but K is equal to A, e to the power of minus EA by RT. What is K? You already know that. K is a rate constant, A is an Arrhenius factor, EA is called activation energy, R is called universal gas constant, and T is nothing but temperature in Kelvin. This is an equation, and these are the factors which involve, or factors in the Arrhenius equation. So this is for 2 marks. They'll ask, write Arrhenius equation, explain the terms. EA by RT, activation energy. Of course, I'll explain to you in the next class what is activation energy and Arrhenius factor. A is Arrhenius factor, T is the temperature in Kelvin, R is a universal gas constant. Coming to the end of session 3, giving an assignment for you so that in the virtual classroom there should be some accountability of writing the other side of the students. You must make a note while you go through the video, go through the session. Session 3, I brought about 4 important questions. Derive the rate constant of first order reaction, derive half life of first order reaction, we just discussed that, derive rate constant of a zero order reaction, derive half life of a zero order reaction. These 4 questions, just make a practice, which I just discussed today's session, very important questions. And of course, physical chemistry is a concept oriented chemistry where the chapter has a lot of concepts. So I hope as you go through the session, you will enjoy the classes, write down the equations. Hope you have any doubts, you can just click to the link which is given and you can upload whatever doubt you have. So hope you are writing there and trying to understand the concepts. You will enjoy, because next session definitely we have a lot of concepts to discuss. about the catalyst, about what happens to the temperature, how to increase temperature and all those things. So hope our next session will be joyful, provided you go to the session 1, session 2 and session 3, and then session 4 will have lot of meaning. So hope you are enjoying the virtually as you're meeting you all. Thank you so much for your listening and going through the session. Hope we'll meet again. Till then, God bless you. Take care, stay home, stay safe.